Hello again, and welcome back to this second part of Lecture 7. This is a quick little one in which we will take a look at the metallicity and relative chemical abundances of stars in the Milky Way. Metallicity of stars in the Milky Way drops slowly as we move from the inner parts of the disk to the outer parts of the disk. We can try and take a look at the figure over here on the right side, and we can see that they start up with relatively high abundances of both iron and oxygen in the inner parts of the disk, and they drop off slowly as we go out to the outer parts of the disk. We can also see that it starts at around 5 kiloparsec. This is not something that is generally true for stars in the bulge and in the bar, so we are only looking at the inner and outer parts of the disk itself. This metallicity gradient throughout the disk is something we also see in other star-forming galaxies, and we often interpret this as a so-called inside-out scenario of stellar mass buildup, where star formation starts in the central parts of the galaxy and then slowly over time propagates outwards, meaning that in the central part, the stars there have had more time to go through multiple generations of stars and with the chemical buildup that comes with that, whereas in the outer parts, they are kind of falling behind on that chemical buildup front. We can also use relative abundances to trace the star formation history. In the last one, we looked at the absolute abundances of iron or oxygen compared to hydrogen. But we can look also at relative abundances of so-called alpha elements to iron and take a look at how that changes across various stellar subpopulations in the Milky Way. Alpha elements are elements that can be formed by adding alpha particles together. So alpha particles, as we hopefully remember, are helium nuclei. And when we add these together, we get this sequence of elements that all increase in atomic number by 2 every time. These elements form rather quickly and early on in the life cycle of a stellar population, whereas iron, as we talked about earlier, needs a quite sizable amounts of type 1a supernovae to really get to enrich the ISM. So the iron abundance rises much later in the life cycle of a stellar population than the alpha element abundance does. And that means that we can use the relative abundances of alpha elements to iron versus the iron to hydrogen abundance to study and tell apart various stellar populations. For example, in the plot that we see here, we can see that the halo stars all have very low abundances of iron and quite high alpha element to iron abundances here. Here, magnesium is used as kind of a representative for or a tracer of the alpha elements, but you can also use like a combination of multiple alpha elements or even go all in and do the closest you can come to a total, measuring as many of them as possible. Further outwards or further along here in time, we get stars from the thick disk here mainly and the thin disk here. And we can see the stars in the thick disk are they almost look like they're falling into this hole where the thin disk stars sit in this diagram, right? We get a higher and higher iron to hydrogen abundance, and of course, since the alpha element production doesn't grow as rapidly as the iron production does at these times, we will get a lower and lower fractional number of alpha elements over iron, meaning that we see a generally downward trend with an upward trend in iron abundance. And this is seen particularly clearly in the thin disk. This is because younger stellar populations in the thin disk are built from gas that has had a longer time to be enriched with iron from type 1a supernovae, and these therefore have a large iron abundance and a low alpha over iron abundance, whereas the ones out here, which we call alpha enriched stars, sorry, now you can see this. Alpha enriched stars are older stars that are formed in a more pristine gas with less iron in it. This can be a little bit confusing sometimes, but we should remember that while the ISM metallicity can develop continuously, the metallicity of stars is basically a snapshot of the metallicity of the gas clouds that they were born out of. There's, of course, also a certain buildup of metals in their atmospheres from their own fusion processes, but this goes quite slowly compared to the general buildup in the ISM. Right. And these specific abundances patterns can then be used to build chemical evolution models, such as we have talked about in lecture 6, but of course with a lot more detail, with a lot more complexity than the very simple toy models that we saw there. And that was it for this one. Thank you for staying with me. It wasn't really that hard this time. It was really short, but thank you for staying with me anyway, and I will be looking forward to seeing you in the next one. Bye.